Hi. Okay. Ladies and gentlemen, today we are going to finish up our lecture on
Yep.
how to get through this section. And let me remind you that tomorrow, or for next class, for you guys, it won't be this class, it'll be the following block day, you're gonna have a quiz on chapter 4. And it'll be all chapter 4 stuff. And we started that grid worksheet yesterday. I'll expect that you'll be able to finish that. I don't think you need me to do that. I'll post an answer key on it before I go to bed tonight. Okay, yesterday we talked quickly about isotopes, and isotopes have the same of what particle?
Protons.
Same protons, different neutrons. Here is one of them that we looked at yesterday. Hydrogen with 1 proton, hydrogen with 2 protons, or helium with 2 protons, lithium with 3 protons. Here is the regular hydrogen with mass number of 1. Here's deuterium with 1 proton and 1 neutron. And here's tritium with 1 proton and 2 neutrons. They're all hydrogen because they have this characteristic, 1 proton. But what's different about them? The number of neutrons, which also means that the mass number is different. How heavy is an atom of oxygen? It depends. We are concerned with average atomic mass. When you look at this periodic table, the red number you see is a weighted average of all naturally occurring isotopes. We call that, the natural occurring isotopes, the abundance, the percentage of each type of isotope that is present in nature. I'm going to tell you something. There's 2 primary isotopes for carbon. The carbon-12 isotope, which has 6 protons, 6 neutrons, and the carbon-14, which has 6 protons and 8 neutrons. When I look at carbon's atomic mass of 12.011, which isotope is more abundant? To get a weighted average that's almost 12, which isotope has to be more abundant?
Carbon-12.
The carbon-12 is tremendously more abundant. Almost all of carbon is the carbon-12 isotope. We don't use grams, actually I use grams per mole. And now, what did I tell you yesterday about AMUs?
They're now just used.
They're now U's, just lowercase u, which is the unified mass unit. But most of my stuff still says AMU.
Ms. Hallstrom?
Yes,
Would you send Anna Stover to the library with her computer?
yes. Now, I think I mentioned this yesterday. Many of you are writing with mostly carbon-12 right now. Is that a true statement?
Yes.
We define an atomic mass unit as 1/12 the mass of a carbon-12 atom. And we chose carbon-12 because it's really easy to, it's stable, it's abundant, it's a really good thing, it just doesn't disappear. That writing on your paper isn't going to disappear by tomorrow because it's reacting with the air. Do you agree? Carbon-12 is very stable, very easy to get to. You guys didn't spend $100 for your pencils, did you?
Yeah.
It's pretty cheap. Graphite is pretty cheap, so it's a good thing to use. Okay, I'm just gonna show you this instead of worrying about this so much. I'll read it quick, don't write this down, I'll show the equation in a moment. You're gonna multiply the atomic mass of each isotope by the abundance. Now, if I give you the percentage of, if I give you abundance as a percent, what do you know about working with the percent? You always have to move your decimal back. You already know that, correct?
Yes.
And we're done, we can express them in AMUs. And in 2 chapters, in 2 units, I'll change that, but today you can express them in U's. Let's take a look at this. The carbon-12 isotope has 6 protons and 6 neutrons. Do you agree with me? What does this one have? 6 protons 7 neutrons?
6 protons and 8 neutrons.
That's correct. So we know that the mass of this one is 12, 13, and 14. Those are the mass numbers. The abundance of this one is nearly 99%. This is 1%, and the carbon-14 is hardly anything. Do you agree? So I'm looking at these percents, and when I do my math, this is just like the weighted grades that I have. Phone's in. The weighted grades that I use for your grade calculations. I use a weighted grade for tests, and what affects your grade the most? Weighted grades in class. Which category affects you the most? Tests. This is like the test category, except I would say 99% of your grade is your test. So this is going to be, this has hardly any impact. Does that make sense to you when you think of it in terms of grades? You don't want me to have 99% for tests, probably. Okay, so let's run through this one, and I think I actually have a similar problem to this one on your, one of the worksheets I gave you yesterday, so we're just gonna look at this. I have an element, we're calling it X. X has 2 isotopes. I'm telling you that one of the isotopes has a mass of 10.012 atomic mass units and a relative abundance of nearly 20%. So now looking at that, let's say it has a mass of 10 and about 20% of it has a mass of 10. Do you agree with that statement? Then next, I've got one with a mass of 11 and it's about 80%. When I'm done, do you agree that my atomic mass, my weighted average, needs to be between 10 and 11? Which is it going to be closer to? 11. Does that make sense to everyone? Okay, so when we're going to set this one up, I'm going to write a little bit up here too. When we set this one up, I like to use this format. The mass of our first isotope times what I'm going to call the relative abundance of the first isotope plus the mass of my second isotope times the relative abundance of my second isotope equals, can I see that? Atomic mass. So this is a handy thing to think of. If I have 5 isotopes, I would just have 1, 2, and then 3, 4, 5. Does that make sense to you? So they already put these numbers in here, but I'm going to put the numbers in up here. My mass of my first isotope is 10.012 unified mass units. Do you agree with that? And my abundance was, shall I write 19.91 or 0.1991? Now, this number is a relative mass, and as a relative mass has no units. You don't get to write down unitless numbers very often, but this one literally doesn't have a unit. Are you clear on that? And then my second mass is, thank you, 11.009 times 0.8009 equals, they've done our math for us, 10.810 atomic mass units.
This is on a somewhat unrelated note, but if one AMU is equal to 1/12 of a carbon-12 atom, then wouldn't that mean that it's basically the weight of exactly 1 neutron?
Yes and no. If we round to 1, if we round to the nearest whole number, then yes it is. Because our masses, when we're dealing with unified mass units, we define a proton as having a mass of 1 AMU and a neutron as having a mass of 1 AMU. Yeah? Okay, did everybody get that? Take a pause. And I really don't care about this too much. Blah, blah, blah. Periodic table, guys, you don't need to write this down, we got a whole unit on the periodic table. We do need to know one thing. This way are periods, this way are groups or families. So that's like it. Each one in a group has different numbers. We got a whole unit on this. Okay. Now, I would like you to please take out that sheet I gave you yesterday that looks like this. It's the one that says Chemistry, Chapter 4, mostly Chapter 4. And I would like you to do question 12. Let's do question 12. Is it still going? Yeah.
Okay.
I'm sure that freaked everybody out by doing that now. Okay, ladies and gentlemen, if you think you know what's going on, you have my permission to ignore me. And work on question 12 on your own. Is that clear? Question 12. Let me shut this off so it looks better on my screen. Question 12 says, I have two isotopes of nitrogen, nitrogen 14 and nitrogen 15. Look at the atomic mass, the weighted average for nitrogen on the periodic table. What is it going to be closer to? 14. And we can see we have 90-some% is 14. So I'm going to take the mass of nitrogen times the relative abundance, which is 0.9963, plus the mass of nitrogen times,
Need some tea? Or
I
coffee?
need some coffee. Can you guys give me coffee? Coffee break.
Which one would you like?
I'd like something flavorful and caffeinated. Now, here's a little problem. It says the rest is nitrogen 15. What the heck will the rest be?
100% minus the.
Yes. Or if I moved it to relative 1 minus, either one. So I'm gonna have 0.003 set, is that right?
Yeah.
Or that's not percent, is that my relative? Did I do that right?
Yeah.
Okay, now, it's math time.
14.04.
I want to tell you something as we're looking at these. When I'm using mass numbers that are whole numbers like this, those, in this case, have infinity sig figs because I haven't rounded it. It is just how many protons plus how many neutrons, which is a count. Do you agree with it? So this one has 4 sig figs. What does this have? 2. So I can only report this to 2. Yes?
What are we supposed to do with ones? Is that 14U?
Mm-hmm.
Yes.
Yes.
Is the 15 supposed to have a U too?
Yes, it is.
Okay.
I was thinking about coffee, so I forgot to write it down.
It's all good.
Sorry. I can already know what the answer's gonna be. It's gonna be 14 U's. Because we can only report to 2 sig figs. Do you agree with that statement?
Yeah.
C.
What if I told you I wanted you to report to 2 decimal places? Who's got it?
14.
What'd you get? 13.99 when you did this?
It's wrong.
Actually, it's 16. That's 14.0.
Yeah, it's gonna be between these two. Because it's gotta be between 14 and 15, do you agree?
Yeah.
So that's what we've got. Do you agree with that number right there? But since I have to report to 2 sig figs, since this has 2 sig figs, this is what my answer would have to be. Okay? I would like to do number 13. I'd like to do number 13. This is gonna be similar to a lab. Ladies and gentlemen, if I have two isotopes, what do my two isotopes have to add up to? 100%, do you agree? So I have to have a total of 1%. Or one for relative. 100 for percent and 1 for relative. Do you agree with that statement? On this particular problem, this is gonna be the same numbers as we used earlier for an example, but I'm asking you to solve for a different variable. I'm told that I have an atomic mass of 11.01 at a 0.8020 abundance. And I'm also told that I have 10.81. I don't know what this is. Or did I get that wrong? That one goes over here. 10.81 right here. And this is the number I'm looking for. How do I figure out what number goes right here? I'm getting 0.1980. Is that correct?
Yeah, it gives us that too.
Oh, it gives you that one too? Okay, 1980. So for this one, I'm trying to figure out this number. How are you gonna do that? Go. I won't punch numbers for you, make sure you can do these. Now this is just basic PEMDAS, do you agree? So you're gonna do this first, then I'm gonna take this number minus this. Then that'll be on this side of the equation. And then I'm gonna have 0.1980x, divide each side by 0.1980. And we know our answer should be in the vicinity of 10. Go. I hear clicking everywhere. What'd you get? 9.99?
9.
9 what?
Well, it'd be 9.9998, and then pretty much just 9 cents.
Okay, you only have 2.
Yeah. No, we can have, and this one we can have 4. So it looks like 10.00. Do you agree with that? Does everyone agree with that? Okay. Very good. So that's how you do atomic masses. These aren't too hard. I'd like you guys to quick solve number 4 because this one has 5 isotopes. 14. And I see that I have, my lowest value is 64 grams and it goes up to 72 grams. So my answer needs to be between 64 and 72. Do you agree with that?
Yes, ma'am.
That's a quick check you can do to make sure you're in the ballpark. Hey, here's an equation, or a mistake I see a lot. Do the math. Everybody does the math. You get an answer. It's going to be between 64 and 72, and then you divide by 5. Because when you hear the word average, you always think you have to divide by the total number, but you don't do that with the weighted average. Do you agree? All you do is multiply whatever that percentage is. You already did that percentage. That's your percent abundance. Okay, get that one done. You may stop this now because we're going to do a couple of practice problems and then we're going to talk about the lab.